Okay, welcome to the last session for today. So our next presenter is currently employed as a research scientist specialising in modelling and simulation of physical systems. With robotics being his first love, in 2011 he finished his dissertation on hard real-time motion planning for autonomous vehicles. Please welcome Andrew Walker.
Thanks very much, everybody. So my talk today is about managing scientific simulations with Redis Queue. And so I have two kind of disclaimers at the start of my talk. The first is that this is most definitely a beginner talk. If you've done any parallel computing or distributed computing stuff, all of this should be pretty much old hat. The other kind of caveat is that I'm certainly not the developer of Redis Queue, but I certainly think you should go and check it out. It's a fantastic module. It's really useful for doing this kind of stuff. So just to give you a quick outline of the stuff that I want to talk about today, I'm going to give you a quick rundown on some of my thoughts on scientific simulation, talk about some Python tools for doing that kind of stuff, talk about Redis and Redis Queue, but probably more importantly, I just want to, for those of you who don't do a lot of this type of work, I want to make it very clear what the difference between parallel simulations and distributed simulations are. So the picture up the top is very much the parallel case, where you have a single Python process that will spin up a number of worker nodes, and that's all running on a single machine, a single physical machine. The second diagram is very much the distributed simulation case, where you've got a single Python process that spins up multiple worker nodes, and some of those nodes could potentially be on a physically different box. Give you a quick rundown on some of the things that relate to building robust simulations, although there's probably not time to do too much of that, and talk about some of the caveats of solving this problem the way that I have. So, I'm very lucky to have the position that I do. I get to work with some absolutely amazing scientists, and they work in a huge number of fields. I work with chemists, biologists, physicists, mathematicians, engineers, and a few computer scientists, not too many. But the one thing that they all have in common is that they solve big problems. Not necessarily computationally big problems all the time, but they're certainly big science problems. One thing that I have learnt is that scientists really just want to do science, and they certainly don't care how I help them when we collaborate together, get solutions to their problems. Which is fantastic for me because it lets me pick the tools that help me solve my problems in the simplest way. So what's a scientific simulation? So this is the Wikipedia definition. Simulation is the imitation of the operation of a real-world process or system over time. So at the simplest level, you can think of a simulation like flipping a coin, and you can imagine some kind of things that you might want to observe in such a simulation, like how often does it come up heads, or on average, how many coins do I need to toss before I'll see 3 heads come up in a row. At the very other end of the spectrum, simulation covers things like, say I want to spend several $1 billion building a Large Hadron Collider. You know, I really want to know before I go building something like that it's absolutely definitely going to work. Okay, so this class of solutions using Redis Queue solves a fairly niche problem. So we're really not interested in the case where you can solve problems with a single Python process. Although Python is great for doing that already, we've got tools like NumPy, SciPy, Cython, Number, and a whole host of other optimization and profiling tools. We're not even interested in that single machine case, although that's mainly what my demonstration will focus on today. Python ships with a multiprocessing module, so batteries included, and so there's not a whole lot of need to talk too much about that. Coming from a predominantly academic background, and I'm sure there's people in the room who come from similar kinds of backgrounds, I'm not interested in talking about supercomputers either. Most supercomputers rely on very specialized scheduling tools and job queues. And at least from my perspective, a lot of the problems that I need to deal with, it's not really appropriate to solve them in the cloud, mainly for business reasons that relate to IP or security issues. So this is kind of the case that I find myself in a lot of the time. We've got about 20 to 50 cores on something like 5 to 10 physical machines. So if you've got a rack, you can imagine that's about one rack worth of gear, or even if you've got desktop machines now, you can imagine that fitting on 1 or 2 desks. All right, so what's out there for doing this in Python? So has anybody used IPython Parallel? Okay, one person. If you're a science person, the absolute first place to go to do any parallelization, if you're an experienced developer, is IPython Parallel. There have been a number of really great talks at the last couple of US PyCons about high-performance computing, and I strongly recommend you go and have a look at that, and the IPython talks as well. It will give you access to a cluster of machines using SSH, MPI, PBS, and a number of other scheduling and communication mechanisms. Has anybody used Celery? People coming from the web development area? So there's a few hands go up. Celery is a bit more like what I'm going to talk about today. It's a job scheduling queue. Most of the time you attach a decorator to a Python function, and that will actually push that. When you call a function, it will push it into a queue that a number of workers can come along and consume. There's a number of other options, but again, my suggestion is that you go and have a look at particularly Ian Osveld's high performance computing in notes from Euro SciPy 2011. There's a couple of other message queuing based systems as well that might be interesting. So why might you choose not to do something like that? Well, it turns out that quite often there's a fair bit of configuration and tweaking that you need to go through. Even for the IPython Parallel stuff, you've actually got to go and find the specific configuration file, set it up to use your transport mechanism. Celery can be even worse. I spent a week fiddling with the internals of Celery, trying to match up some kind of storage mechanism with the right kind of message queues. And maybe this perception of being difficult to get up and running is just something that applies to me, but I've seen other people, really great developers in the Python community, struggle with some of this stuff. Even worse from my perspective, because I work with scientists, if I get something like this set up and running for them, they don't want to have to sit there and babysit my work, making sure that their simulations haven't fallen over. Okay. So what was I looking for in the kind of ideal tool for solving these problems? It's really something that you can get going in an afternoon. So I figure that's about the length of time that I've got to actually teach somebody how to understand something really well. And if it's that short, they've got some chance of actually remembering how to do it. Ideally, it had to have no configuration file editing, and the only thing I had to do to get my demos up and going was I had to open an exception in my firewall. And the absolute one thing that I didn't want to have to do is configure that message broker. Okay, so that's what I wanted, and this is kind of the solution that I ended up with. Redis is the core, forms the core of the Redis Queue module. It's actually a data structure server that lets you associate values with keys. Now, I can honestly say that I know almost nothing about Redis. And in this case, it's probably an advantage that I don't know anything, because it just hasn't fallen over. It almost always stays up, and it's just worked. It's written in C, bindings to most popular languages, and certainly easy to access from Python. If you're going to use Redis, just raw Redis, it looks something like this. So if I'm trying to bind to a Redis server running on localhost, I open my connection, and then I can associate some kind of value, in this case a string, with a key. And I can then pull that key back out. If I need to do that later, I can actually close my Python session and then open it back up and pull the same value back out with that key. All right. So what's this Redis queue? So one of the great things about Redis is that it actually lets you use multiple data structures. So I can associate a list, a mapping, a set, or a queue with one of those keys. And that means that I can actually push a job, which a job in this context is just a function and its arguments that you're going to call with that function. The beauty of Redis is that it's pure Python. That means anybody can actually read and understand the code, which makes it perfect for scientists and trying to debug the harder things. And it also provides a really clean API and what Kenneth Reitz would call an API for humans. So one of the simplest examples, just in case all my demos fall over, looks like this. So you actually, you set up a queue and connect to Redis on localhost. You look up you have a string to the name of the function. So in this case, look up the module operator and the add function in that module, and then you can pass it some arguments. That gives you a handle to the job, which is, in some languages you might call that a future. It's a promise that you're going to, or a promise that you're going to get an answer back at some later time. So I can wait a little while because, hopefully it won't take more than a second to calculate 2 plus 3, and then I can print out my answer. To have all this work, I actually need to have something that's coming along and consuming those jobs that I'm pushing into the queue. So I can launch some workers. So by default, Redis Queue workers will listen on localhost to the default queue. If I want to do something a bit different, I can launch the worker on a simulation queue at a particular, and pointing at a particular instance of Redis. So, once you've got a whole bunch of these workers spun up, one of the things that you really want to know is, have any of them fallen over? Are my jobs passing or failing? Are they throwing exceptions? So an important part of any parallel simulation is some kind of monitoring tool. Redis comes with two solutions for that. One on the command line, which is rqinfo, and the other is the RQ dashboard, which is a little web app. So fingers crossed, my live demo is actually going to work. Come on. All right. Does anybody here use Tmux? Just a couple of people. So this might be a bit interesting for some of you. Tmux is a terminal multiplexer. It lets me run multiple terminal sessions on the screen at one time. It's going to be great for this because I need to try and get as much stuff squashed onto the screen as I can. All right. So I can fire up my Redis Queue worker, and you can see that it's listening on the default queue and it's connected to Redis on localhost. And you can imagine that in my second terminal session, I could easily SSH out to another machine and I could run RQ worker on that machine. So just to show you what that might look like, there you go. I'm connecting to the Redis running on localhost. So very much the same as the first one, just slightly different syntax. All right, so now I need something to actually push jobs into my workers. So I'll fire up a quick session of IPython. Can everybody read that? Yep. All right. So some basic imports. Create my queue. Link it to my connection to Redis. And at this point, I've actually got enough stuff to actually sending jobs to my workers. Now, the great thing about this is that's pretty much the same amount of code that you would have needed to do this with multiprocessing. There's a little bit more setup outside of Python, but I figure that I can teach pretty much anybody those 3 lines of code. All right, so let's actually in-queue a job. And you can actually see that on one of the workers, the job has actually run, and you can see the result. It's a bit hard to see. I can run a second job, and you'll see that it'll actually try and balance that out between the different workers a little bit. So do something a bit different. So just run a sleep, and eventually it will finish. All right. But the other thing is that I can actually create the job in queuing functions or tasks into the queue, hands me back a job handle, which I can then pull the results out of. All right, so that's not really a scientific simulation. It's just kind of executing stuff one thing at a time. So let's kind of scale this up a little bit. Just to make this a bit easier for me to manage, I've kind of prepared one earlier. Has anybody heard of the traveling salesman problem? This is a problem from graph theory and optimization and complexity theory that's pretty common. So the basic idea is that you set up a graph and each of the nodes in the graph represent a city, and each of the edges in the graph actually represent some cost of traversing between those cities. And what you're trying to do is actually find a tour. That's a path that visits every single city in the graph and returns back to the starting city. Really what we're looking for though is which of all possible tours is actually the shortest. So, it's not hard to imagine what kind of things that you would have to do to actually make something like this work. So there's just a little blob of code that calculates the length of a tour, and there's something that actually, given a bunch of tours and a graph, which one of those tours is actually the shortest. Okay, and so this is the naive solution, which is basically to enumerate all possible permutations of cities. That gives me all the tours that I could ever want to run. And then I can actually just calculate which one is the shortest. So let me do this now. And so that was pretty quick, right? So that was with a complete graph with 8 nodes. So let's make this 20. Okay, you can see my kernel busy flag in IPython. Busy, busy, busy. All right, let's just say for the moment that that's way too slow for my purposes. And this is what tends to happen when you're actually building up these simulations. You start with a really simple, small problem, and you grow it to a certain extent, and then you can't grow it any further because it's too slow. So what's a different way of solving this problem? Okay, well, one way to do it is to actually start looking at, all right, I don't have to explicitly enumerate all permutations. I can just randomly generate a whole bunch of them. So there's great tools in NumPy for generating random permutations. And so if I do that on that big graph again, what I can get is an approximate solution. And in many cases, that's enough. You scientists will be happy with that. Anybody who's actually done this for real and understands the traveling salesman problem, this is absolutely not the right way to solve this problem. There's dynamic programming techniques that will solve it much more efficiently, and there's really great tools out there for doing it. What this does show, though, is it shows how the class of problems that I'm interested in and care about scales. All right, so that's a simulation, but let's actually throw that at Redis Queue. All right, so the only change that I really had to make to the previous code was to refactor it out into a module. So it's sitting in that naive TSP module. You then have to make that code available to all the workers. One way to do that is by running all your workers locally, like I'm doing now. If you're running distributed, you can use network file systems. You can actually install the module on all the machines that you care about. How you do that will depend a little bit on how you're set up to do this. The other comment about this is actually polling and waiting on some of these jobs is probably not an ideal way to do this. An alternative is to actually get them to write out results files to disk somewhere. Again, if you've got a network file system or a database that you can drop your results into, that's perfect. All right, so I'm going to fire this up, and you can see the kernel's busy, and if you're standing next to me, you could probably actually hear the fan on my computer go crazy. You can actually see the results of some of the nodes start to show up, and what I'm going to do is fire up rqinfo. So you can actually see the state of the master queue and what each of the workers is doing. So both of them are busy at the moment. Okay, so that's kind of a boring command line interface to that. Let's see if we can get a bit more information. So this is the RQ dashboard, and again, you can see the same kind of things. There are my workers, there's my queues, there's some jobs left in there. And then these are the actual functions that are still left to run in my queue. All right, so we'll let that run. So, even though this approach is really simple, and it's great for teaching to scientists because they can get going in a really short space of time, it's got a few limitations. You really do have to intervene to add robustness. One of the great things about Python is that doing that is actually fairly easy. You can write some decorators that will abstract away things like writing to your database or writing to a file system, or augmenting your results with some extra data. You do have to actually distribute that source code to all the workers. This is one thing that's a bit curly. It shows up sometimes when you're working with Celery as well and some of the other message queuing tools. Everything that you pass across to a remote machine has to be serializable. So that means that you can't have used closures, you can't have captured variables from the scopes that you've defined your functions in. And that applies to arguments to those functions as well. It can potentially be just a bit memory hungry. So if I went back to my last simulation, I'd actually created my graph and then basically made 500 pickled copies of it and stuffed them into Redis. So that's not the greatest way to do this. So you may want to think about slightly more efficient ways to actually transmit that information around. For me, this is a bit of a pro and a con. So each of those Redis workers, every time it starts to run a job, it will actually fork a new copy of Python. Now, some of my stuff tends to be C extensions, which can be buggy. They can leak file handles, they can leak socket handles, and they can leak memory. And so it's nice that the operating system just comes along after each job has finished and cleans everything up. There's a couple of other little kind of corner cases about Redis Queue workers that get killed off too aggressively, leave some resources lying around. So there is a bit of work that you need to do to tidy this up to make it a finished solution. And as is the case with anything that is effectively an optimization, you really need to think about whether you want to go to the extent of doing this stuff first. If you have one core and you add, 9 more cores, the best that you're going to hope to improve your performance by is a factor of 10. Make sure that you know what you have really is a problem. Is it if you actually use something like NumPy or SciPy or some smarter data structures and algorithms, can you actually remove the need to go to a parallel simulation in the first place? And understand that doing this stuff actually is expensive. So everything can fail now. So your worker nodes can fail, the network connections can fail, and you've got to actually make sure that all of that stuff stays in a sufficient state of readiness that your simulations will run. And make sure you can't cheat, because a lot of times, especially with this class of problem, there are better solutions. Any questions?
I just have a question about serializing the functions or methods that you pass in.
Yeah.
Can you get around that? 2 questions. First, does it throw an exception or something if you try and pass?
It will tell you that it's not pickable. There are some ways to work around that to a certain extent. If you've decorated a function, so if I go back.
So yeah, the second part was can you pass in a callable class object or something like that to avoid that constraint?
The callable classes, I'm not entirely sure. One of the reasons to actually use the strings to actually refer to the functions is that it works around some of those problems about pickable functions. It will actually go look the final function with any decorators up, and so that helps there. but the callable class, I'm not sure. It may be that you can subclass some of the internals of Redis Queue and make that work.
Yeah, I'm just wondering about if you had algorithms that required a lot of configuration or something like that, how you'd pass that around.
It may just be easy to transmit those things as files or as entries into a database. Or, in fact, given that you've got Redis running, it may be just as easy to stuff those arguments into Redis.
Were there any more questions? We've got a couple more minutes. Yeah.
Hello. This might not be the intended use of this, but have you encountered any synchronization problems? Does this do synchronization properly?
Sorry, can you say that?
Synchronization? Is there any issues with that?
And so one of the things that I try to do with a lot of these things is you try and break each of your jobs down into atomic work packages that don't rely on anything else. And so you've kind of you've stepped around the synchronization problem. Now, that certainly won't work in every case, but given that most of my simulations are Monte Carlo simulations where the units of work really are atomic and not interdependent, I don't care. So again, it depends a little bit on your problem space.
So one other thing that comes to my mind when we speak about the word simulation is trying to run the same thing on so many different set of input values,
Yep.
which could also be looked at in another way as a different test cases.
Yes.
So have you ever had a chance wherein you have used something like a test runner, maybe PyTest, in order to do these simulations and then generate report?
No, but that actually sounds like a good idea. We certainly have lots of test cases for some of the scientific software, and it probably just does make sense to reduce the time that it takes to check everything by doing something like that. Yeah.
Hey, thanks, great talk. When you use threading,
Yep.
you get trouble with debugging when you try to import PDB set trace. Is it easy to just put your breakpoints here?
I don't think that would work at all. I'm honestly not sure. Most of my experience with this has been write, test, debug on a very simple test case first. And you know, one of the places where something like that might be interesting is if I have a case, a simulation that fails, you can see that when it was running, there was actually a default queue. Jobs that fail will actually jump into the failed queue, and I can actually go back in and pull out the arguments that I passed to those things. Now, all things being equal, I should just be able to copy those arguments and try running that particular case on my local machine again, and it should behave the same way. For Monte Carlo simulations or things where there's some randomness involved, there's some quirks of doing that.
This is more of a statement than a question. There is a library called PyCloud, the idea being you write functions on your local machine, you push them off to some remote service to actually execute them.
Yep.
As part of that library, they re-implemented part of Pickle that should allow you to serialize things such as functions, etc.
I know that the IPython parallel does a bit more of that kind of thing as well. So, you know, this is very much a first cut solution that you can start prototyping and playing with some of these ideas. At the point where you've got it going and it doesn't work any longer for you, it's definitely worth upgrading to one of these better tools.
All right, thank you for your talk, Andrew. To say thanks, we've got some coffee and a coffee mug, and if you could join me in thanking Andrew again. Thanks.